we're going to dive right into chapter 17 and talk about enols and enolates. So far, we have been thinking about carbonyl compounds as electrophiles, and they are. But today we're going to start thinking about the two things. One is the tautomer of a carbonyl compound, which is called an enol. So this is a ketone. This is an enol. Notice that the ketone and the enol are isomers of each other, and they differ in the location of a proton. Here, with the ketone, we have a CH sigma bond, and in the enol, where that proton is, we actually have an OH sigma bond. And then in the ketone, we have a carbon-oxygen pi bond, and in the enol, we have a carbon-carbon pi bond. Now, if you go look up bond energies, an oxygen-hydrogen bond is stronger than a carbon-hydrogen bond by a modest amount, but a carbon-oxygen pi bond is even more stronger than a carbon-carbon pi bond. So it turns out that the ketone form, or what we'll call the keto form, is more stable than the enol form. The oxygen-carbon pi bond is more stable than the carbon-carbon pi bond because of oxygen's electronegativity, which literally means electrons on oxygen are held lower in energy. All right. So the process of going from the ketone to the enol is called tautomerization. These two species are called tautomers. And that's a word we use to mean isomers that differ in the location of pi bonds and protons. There are ways to get to the enol under acidic conditions, but most relevant for us today will be basic conditions, so I will show you that. And for this, we need to have some tools for talking about carbonyls. I'll call the carbonyl carbon C, and then adjacent to that is the alpha carbon. And it turns out that the proton that is alpha to the carbonyl carbon is more acidic than you would expect for a proton on an sp3 carbon. The pKa of that proton is around 20. Now, normally, if you remember, and you can go look it up on your pKa table, a carbon-hydrogen bond on an sp3 carbon has a pKa of around 50. So this is 30 orders of magnitude, 10 to the 30 times more acidic than a typical sp3 carbon-hydrogen bond. And the reason for that is easiest to rationalize if we draw the conjugate base. So let's remove the proton from the carbonyl carbon. Of course, the position of this equilibrium between the base and the ketone versus what I'm going to draw you now, the conjugate base, that's going to depend on the strength of the base. And we're being very general. We haven't said what that is. But let me draw for you the conjugate base of our ketone, where we've removed a proton from the alpha carbon. And this base, as you can see, has a lone pair on the alpha carbon, and that's conjugated now to the carbonyl carbon such that we could draw a resonance structure that looks like this. Okay? You can get to that resonance structure simply by moving the electrons on the alpha carbon over to form a pi bond between alpha and carbonyl carbon. and then moving the electrons on the, from the carbon-oxygen pi bond up onto the oxygen. These are two resonance structures. The conjugate base of your ketone is resonance stabilized. Remember, resonance spreads out electron density. It does this for the molecule, the conjugate base we're talking about. There's two pairs of electrons that are spread out. There's the lone pair electrons that are spread out onto the alpha carbon and the oxygen. And then there's the pi electrons that are spread out between the carbon-oxygen bond and the carbon-carbon pi bond. Two pairs of electrons that are resonance stabilized, two pairs of electrons that are lower in energy than they would otherwise be. And that resonance stabilization is what makes this alpha proton more acidic than expected. Let's be realistic, a pK of 20 is still really not that acidic. You need a strong base to completely remove this proton. Nevertheless, the proton that's alpha to the carbonyl carbon is more acidic, and the simplest way of thinking about that is to realize that the conjugate base is resonance stabilized. We're going to call this conjugate base an enolate, and that has reference to the fact that its other conjugate acid, if you add the proton on the oxygen, so I can show you how to get to the enol, involves protonation on the oxygen, and then that gives you the enol. And of course, the equilibrium between enolate, enol, and ketone is going to depend on a couple of things. First, the fact that the keto form is more stable than the enol form, but then it's going to depend on the base strength, whether we have a majority of enolate formed or not. Okay? Questions about the enol and the enolate? All right. While we're at it, let's talk about alpha proton acidity. But we're going to come back to this question of what the equilibrium constant is for formation of the enol, because that's going to be really important for how we consider reactions involving enolates. We'll see that protons alpha to carbonyl carbons vary in acidity over a wide range of values. But fortunately, they vary in a way that makes sense if you're already used to thinking about how reactive a carbonyl carbon is. So let's just look at some pKa values. I'm going to draw a carbonyl compound, and we're going to draw these in sort of increasing order of acidity. So here is an amide. The alpha proton we're talking about is here. The pKa value I'll put here. pKa of the alpha proton. And the pKa of the alpha proton on the amide is around 30, which is really not acidic. And one way you can rationalize this is by going back to the enolate resonance structure and realizing that in order for that negative charge to be stabilized by resonance, I have to donate electron density into the carbonyl carbon. You would predict that if the carbonyl carbon is more electron poor, this resonance structure, where electrons are donated into the carbonyl carbon, should be more important and more stabilizing. Whereas if the carbonyl carbon is electron rich already, then donating electron density into the carbonyl carbon should be less stabilizing. So let's just look at one of the resonance structures of the enolate for the amide and see why this might be so much less acidic than the ketone. Okay, we can draw a resonance structure where lone pairs donate into the carbonyl carbon like this to generate, and sorry, one of those protons should be in R. However, for the amide, there is an alternate resonance structure in which lone pairs on the nitrogen are donating into the carbonyl carbon to give you this resonance structure. That tells you that the carbonyl carbon of the amide is already electron rich, and so it's not as favorable for the lone pairs to be delocalized by resonance. In other words, if you have, and in general what you will see is because of the lone pair on the nitrogen and the fact that nitrogen's less electronegative, say, than oxygen, nitrogen is a good electron donating group, and carbonyls with good electron donating groups directly attached to them are not very electron poor, they're not very reactive, and their enolates are correspondingly unstable. The carbonyl carbon for the amide is not very reactive because of the influence of that electron donating group. It's not that attractive for a nucleophile to attack the carbonyl carbon. And for the same reason, it's not that attractive for a base to remove the alpha proton because the carbonyl carbon's already decently electron rich, which decreases the driving force for this kind of resonance stabilization. Okay, are you following that reasoning a little bit? Okay, questions? All right, so let's predict what would happen. What do you predict for the ester? Put an oxygen here instead of a nitrogen. Is an oxygen, an OR group, a better or worse electron donating group than nitrogen? Worse, why? Oxygen's more good. Oxygen's more electronegative, meaning the electrons held on oxygen are lower in energy and less available to be donated. So, yeah, the ester is still an electron donating group, but not as good of an electron donating group as in the case of the amide. And so what would that prediction be for the acidity of the alpha proton? More acidic or less acidic? More or less is easy to get confused on. Remember, we're all talking about the electron poorness of the carbonyl carbon. If the carbonyl carbon is more electron poor, the alpha proton should be more acidic. And indeed it is by a factor of about 100,000. And we could draw, I won't, but we could draw the resonance structures here to verify that fact, okay? Now, if you go to the ketone, which you've already seen, what that pKa is, I already told you it was 20. A methyl group is an electron donating group, but not via resonance. We've talked before about how sp2 carbons, like the carbonyl carbon, are more electronegative than sp3 carbons. So the more sp3 carbons you have attached to that carbonyl carbon, the more the sp3 carbons are able to donate via an inductive effect into the carbonyl carbon. So the methyl group is an inductive electron donating group, but it's not as good of a donating group as a resonance electron donating group. So you expect, as you've learned, the ketone to be more reactive than the ester. It's easier for a nucleophile to attack the ketone than it is to attack the ester. Similarly, it should be easier for a base to remove the alpha proton. And again, the rationale for that is that if the carbonyl carbon is more electron poor, yikes, that makes this kind of resonance stabilization even better, because this resonance stabilization involves donating electron density into the carbonyl carbon. All right, so you've got that order: amides, esters, ketones. For the same reason, you're going to expect aldehydes to be a little bit more acidic than ketones. The pKa for this simple aldehyde is again is around 17. That's a factor of 1,000. The proton is not an electron donating group, so the carbonyl carbon of the aldehyde is relatively electron poor, and that means that resonance stabilization of the resulting enolate is more important, and therefore the resulting enolate is more stable. All right, more stable enolate leads to more acidic alpha proton. And notice that we're getting in a range of pKa's that are values that are like things that you've seen before. For example, OH minus, who has a conjugate acid water, pKa 16, should be able to remove maybe 1 out of 10 protons from 1 out of 10 aldehyde molecules. Okay, and we can get even more sort of creative and exotic. There's a class of carbonyl compounds that we'll deal with later, in which the alpha carbon is alpha to not 1 but 2 carbon oxygen pi bonds. What I've drawn for you here is called a beta dicarbonyl compound, or what will follow actually is a series of beta dicarbonyl compounds. This one is called a beta diester. Why is it called beta? Well, here's a carbonyl carbon, and then you've got a second carbonyl carbon, beta to the first. Doesn't matter which one we say is the carbonyl compound, they're identical to each other. And the pKa for this alpha proton that's adjacent to 2 esters is 13. That's pretty acidic, actually, for a CH bond. That's acidic enough that you'd expect OH minus or OR minus as a base to be able to remove 100% of the protons. The reason for this is pretty straightforward. You can see that the conjugate base with a negative charge, there's 2 hydrogens there, with a negative charge on the alpha carbon, has 2 possible alternative resonance structures in which a negative charge is on an oxygen. Here's one of them. And then here's the other. More opportunities for resonance delocalization means the electrons are spread out over a larger space. That's a stabilizing effect. Spreading out electron density is always stabilizing. That actually has to do with MO theory and quantum mechanics. It turns out that wave functions of electrons that are spread out over more space have lower kinetic energy. And in any case, having that negative charge delocalized on 3 different carbons is more stabilizing, and 3 different atoms, 2 of which are oxygen, is more stabilizing than the enolate structures you've seen so far, where the negative charge was either on a carbon or an oxygen, but not 2 oxygens. Okay, so the effect of the second carbonyl group gives you an even bigger benefit. Now we can do some interesting things like mixing and matching carbonyl compounds on these 2 carbonyl carbon and beta carbons. For example, here is a beta diketone, And here is a beta keto ester, where the ester has a ketone beta to it. If you had to predict, based on what we've discussed so far, relative acidities, what do you predict for the beta keto ester versus the beta diester? More acidic, less acidic? More, right? Why is that? Same reason why the ketone is more acidic than the ester. Remember, the electrophilicity of the carbonyl carbon is going to determine the stability of the resonance structure. If you've got a good electron donating group on the carbonyl carbon, that's going to decrease the stabilizing benefit of resonance. So here we have two esters. Here we have an ester and a ketone. Ketones are more electron poor than esters. Ketones are better electron acceptors in the conjugate base, meaning that the resonance structure in which the negative charge is delocalized out on the ketone is going to be quite favorable, more favorable than up here where the only option is to be on an ester oxygen. So yeah, we do predict that the beta keto ester should be more acidic than the beta diester. And in fact, that number's pretty low as well, pKa of 11. How about for the beta diketone? More acidic or less acidic than the beta keto ester? Even more, right? Good. And this number's ridiculous. Like, this is a ridiculously low pKa, 9. That's low enough to be removed by ammonia or neutral amines, which is really out of this world for carbon-hydrogen bonds. Okay, that's good. So question so far about alpha proton acidity. I'm going to answer this question now before you've asked it. One of you is going to come to my office hours and ask, I get everything you just said about acidity, but I don't get what I'm supposed to do with this problem. I actually don't know the pKa for that one. You could look it up if you wanted to. And the reason that looks difficult to you is because you're just used to looking at CN and thinking, okay, that's a nitrile group, or that's CN minus is a nucleophile, so that just comes as a package. Fine, but the problem becomes trivial if you actually draw out the Lewis structure of the CN group. What do you notice about those CN groups? What do they got? Go ahead.
Oh, they're going to take a lot of the electrons.
Yeah, they can be electron withdrawing groups. How did you know that? Yeah, you've got carbon-nitrogen pi bonds. You've got an electronegative atom here, pi bonded to the carbon, which tells you that in the conjugate base, you should be able to draw a resonance structure in which you move the lone pair from the alpha carbon to form a pi bond with the nitrile carbon. And then you've got to move one of the pi bonds of the nitrile carbon out onto the nitrogen. This would be one of those two resonance structures. And you should be able to draw another that would help you conclude that in the conjugate base of this dicyano compound, the negative charge is on the alpha carbon and the two nitrogens. I don't know what that pKa is off the top of my head, and I would certainly not ask you to compare the pKa's, say, of this dicyano compound with, say, the diketone or the diester, because we really haven't developed tools for talking about, whether the nitrile carbon is more electrophilic or less electrophilic than your typical carbonyl carbon. But hopefully, once you see the Lewis structure of the cyano group, the mystery goes away. Okay, and we'll see in general the nitrile, the CN group, can be used, is going to have similar types of functions as as ketones. In other words, the carbonyl carbon is an electron withdrawing group that can stabilize a negative charge by resonance, so too with the nitrile group. Okay, other questions? All right, now we're going to talk about, you're going to use that pKa information to make some predictions about the position of an equilibrium between a ketone or a carbonyl compound and an enolate as a function of what base we're using. Now you know the pKa's, this will take some of the mystery out of what we're going to be doing. So let's imagine this ketone, we're just using acetone, and here is the alpha proton. And my base is OH minus. Now, actually, we're back in 351, chapter 2, which you guys all thought was easy, and it, sort of is, where we're going to ask, we're going to draw the conjugate base. You are free to draw the enolate any way you want that is correct. I guess that's not very helpful. You can use either of the two resonance structures for the enolate. If you're drawing a mechanism to show an enolate forming, you can do that in one of two ways. You can remove the proton and have the negative charge go on the alpha carbon, which leads to one of the resonance structures of the enolate. Or alternatively, you can draw removal of the alpha proton, electrons kick over to form a pi bond, and electrons move from the carbon-oxygen pi bond out onto the oxygen. Either of those options leads to either of these two resonance structures, both of which are acceptable. But back to 351, to talk about the acid-base equilibria here, we simply need to identify the acid on either side of the equation and then write down the pKa, which is 20 for the ketone and 16 for water. So you tell me which side dominates at equilibrium. You forgot how to do it, or it's obvious. I'm trying to figure out which option we're dealing with. This is what happens in Sunday school when you ask a question to which the answer is obvious. Like, well, you should just pray more, right? So I'll answer the... No, I refuse. What's the answer? Starting material, right? How can you tell? Strongest acid loses its proton, right? And the strongest acid is the one with the lowest pKa. Water is a much better acid by a factor of 10,000 than the ketone. Therefore, you expect the equilibrium constant to be way, way, way less than 1. And actually, we'll draw a big arrow this way, tiny arrow that way. Probably, for a factor of 10,000, you're probably looking at 99.999%. Is that 10,000, or is it that? Is that the 10,000 one? I don't know. You'll forgive me if I don't have enough nines and zeros there. But that's the idea, is we only have a very, very small percentage of enolate at any given time. So when you use a base that is not strong enough to completely deprotonate the enolate, we call this reversible enolate formation. That's important. It turns out that even though having 0.01% is not enough to do synthesis, if your goal is to synthesize an enolate, think of how many molecules there are in a mole of something. Something around 6 times 10 to the 23rd, right? 0.01% of 6 times 10 to the 23rd is still a ton of molecules, right? It will turn out that we can use the 0.01% of the enolate that forms as a nucleophile in subsequent reactions. If we have an electrophile here, the nucleophile can attack it. That will draw the enolate out of this equilibrium. And by Le Chatelier's principle, that's going to pull more starting material towards the enolate. So it turns out we can use reversible enolate formation to do chemistry with the enolate. And sometimes we will absolutely want to, and I'll show you when that's the case. But first, I need you to understand this concept of reversible enolate formation, which is that there's only a very small amount of enolate formed. Sort of make sense? Okay. Why do we care about reversible enolate formation? Well, the answer is that some carbonyl compounds have more than one kind of alpha carbon. All right? So here is an example of a carbonyl carbon with 2 different kinds of alpha carbons. You got orange alpha carbon and you got purple alpha carbon. Orange alpha proton and purple alpha proton. And there's 2 possible enolates that you can form. If we remove the orange alpha proton, we get the orange enolate, which I'm going to just draw with this resonance structure. And again, that's for now, let's just use OH minus as our base. We're going to do reversible enolate formation. At the same time, we might also remove purple alpha proton to make purple enolate. By the way, notice that the pi bond here in the enolate between purple alpha carbon and carbonyl carbon has stereochemistry. It could be in an E or Z isomer. That is a thing, and chemists worry about it. We're going to pretend like it doesn't exist for the purposes of this class. Right. Okay, that makes me feel better. So I got 2 possible ways this reaction could proceed. In both cases, greater than 99% of my material is going to be in the starting material, and I'm only going to ever form a small amount of enolate. Let me show you what this does for us in terms of an energy diagram. So here is your starting material. Here is the pathway to the orange enolate, uphill in energy. And then the pathway to the purple enolate is also uphill in energy, but we need to think about how uphill in energy it is versus the orange enolate. So let's compare the stability of these 2 enolates. And to do that, I want you to think back to what you learned about alkenes in 351. What would you say about this alkene versus that alkene? Yeah, most of you know that rule. A more substituted alkene is more stable. There's reasons for that we could talk about, but let's just use the rule as is for now. Purple enolate has the more substituted carbon-carbon pi bond, and therefore is the more stable enolate of the two. Now, we have to speak precisely so that we can be understood and not misunderstood. We're not saying that that enolate is more stable than the starting material. We're just saying it's more stable than the other enolate. So in our drawing, if this is sort of the energy level of the orange enolate, let's put the purple enolate just a few lines down from that. This isn't to scale, but this energy difference is smaller than this energy difference. Just reflecting the fact that the orange enolate is less stable than the purple enolate. Okay? So, you're good at thinking about equilibrium. Even though 99% of my material is still the starting material, the ketone and the base, and you know, the base is important because it's the base you choose is what makes the energy landscape look like this. Even though 99% of my material is this, of the small amount of enolate that does form, which is present in a larger amount? Purple, present in larger amount because it's more stable. And this is an important principle. We have more of the purple enolate than, that's not the general principle, than the orange enolate. The general principle is that when you're under reversible conditions, you're going to form more of the more stable thing. So under reversible conditions, we get more of the more stable enolate. And that's actually general in organic chemistry. Under reversible conditions, you get more of the more stable product, period. Has to be that way. How fast it forms doesn't matter, because under reversible conditions, you're going back and forth all the time, and you're eventually going to get a mixture of products weighted by how stable they are. We're going to use this principle later on to determine what the outcome of a reaction will be when we use an enolate as a nucleophile. And we'll need to pay attention to what the conditions are, because for this starting material, if we're using reversible conditions, we're going to get the majority product from this more stable enolate. All right. Let's talk about questions about that before we move on. All right, let's talk about irreversible enolate formation. Oh, I wanted to say, sorry. The more stable enolate, your text will sometimes call basically always call the thermodynamic enolate. Dynamic enolate. I, in the past, have worried about that because I think it's maybe potentially confusing to you. What do we mean by thermodynamic? Thermodynamic is all about relative stability of molecules. It's about equilibrium. So The thermodynamic enolate is simply the enolate that is more stable. People will often talk about, not so much in your text, I think, but you'll hear chemists talk about reactions being under thermodynamic control. All that means is they're running the reaction under reversible conditions so that the product you get is the one that goes through the more stable pathway. Or rather, sorry, the product you get is the more stable one. I'll sort of stick with reversible conditions. I'll try to say more stable enolate, but when you read about it in your text, you may read thermodynamic enolate. Just understand that's what they're talking about. Okay, so those were the conditions for making enolates reversibly. Let's talk about irreversible enolate formation. And in your text, when you form enolates under irreversible conditions, you're going to get as a product what is called the kinetic enolate, and this is a reaction that's under kinetic control. When a reaction is irreversible, product stability does not matter. The product that is fastest to form is the major product because you can't go backwards. And so as soon as you form product, you're done. So it's just a race, and the winner is the one that forms fastest. So there are, let me give you some examples of irreversible enolate formation. And there's nothing magic about irreversible enolate formation. You simply have to choose a base that can quantitatively or 100% deprotonate the alpha carbon. So again, this is going to be a pKa issue. We're going to want to choose a base that's strong enough to make 100% enolate and do so irreversibly. An example of irreversible enolate formation is this beta diketone. We talked about it just a minute ago, but I glossed over the fact that there are two different kinds of alpha protons. You've got the proton that is alpha to 2 carbonyls, and then you've got the proton that is alpha to just 1 carbonyl. Looking at the pKa's, the pKa of the alpha proton, the orange alpha proton is 9. The pKa of the purple alpha proton is around 20. And if you use OH minus as a base, it is fastest and most stable to remove the orange alpha proton. I guess we should draw the purple enolate, which I'll draw in this form. And that happens just comparing the pKa's. Nine here, 16 for water. That equilibrium constant is, let's see, around 10 to the 7th, which basically means we have 100% of this and 0% of this. Yeah, go ahead.
Is that supposed to be the orange one?
Yeah, I'm gaslighting you. That is orange. No, I'm sorry. It is supposed to be orange. This is why I love Notability. Watch this. Ta-da! Whoa! All right. So that's irreversible enolate formation. You form the enolate 100%. okay? It would be correct. This is why sometimes I worry a little bit about the kinetic enolate, the thermodynamic enolate. It would be correct to call this the thermodynamic enolate, because if you look at the other one, the one that we don't form, it's certainly a less stable enolate, for sure. But the orange one is also the kinetic enolate because it's the fastest to form. And this is not a reversible reaction. This is a 100% reaction. And it's not reversible because this proton is very acidic. More acidic than the conjugate acid of your base. Is that, I don't know that I'm making sense here. Questions? All right. Another situation where you can see irreversible. So one strategy for irreversible enolate formation, what I just showed you, is to use a super acidic alpha proton. Strategy 2 is to use a super reactive base. That is a base that is able to 100% remove an enolate. So we need to introduce a new friend to you. This is a base that's used often in enolate formation. We'll start with a simple example, and then we'll move on from there. So carbonyl carbon, alpha carbon. This proton has a pKa of 20. We're going to use a base that's called lithium diisopropyl amide. Lithium's the counter ion. Unfortunately, in organic chemistry, we use the term amide for two different things. Amide can refer to this kind of functional group, and it can also refer to a nitrogen with two R groups, two lone pairs, and a negative charge. I am sorry that it turned out that way. I didn't make up the rules, and it's too late to change it. This reagent, lithium diisopropyl amide, there's two I's in there, the other one is hiding, is sometimes called LDA, right? I'll draw for you the enolate that's formed. And then I'll draw for you the conjugate acid of lithium diisopropyl amide. The proton that gets removed has a pKa of 20 in the ketone. Over here on the nitrogen, when you get to the conjugate acid, which is diisopropyl amine, that has a pKa of 40. So that means the equilibrium constant here is 10 to the 20, meaning, again, 100% quantitative yield of enolate. Irreversible, because the base is simply strong enough to remove that proton. Right. So what does this do for us? If we go back to the same situation that we saw before, the strength of that base is going to totally remodel this energy landscape. All right, so I'm going to copy this. Oops. And then we're going to show you, I'm going to show you how we remodel that energy landscape based on the strength of that base. But before we do that, we'll go ahead and take a break. So let's take 5 minutes or so, and then we'll start back up.